Hey guys, for calculus, this is from 3.5 and 8.7. And for pre-cal, when we start learning calculus, this comes from 4.5. We're going to recap infinite limits, and then we're going to start seeing L'Hopital's rule, okay? I've been telling you about L'Hopital's rule since limits because it is a procedure that's going to make solving those complicated limits a lot easier. But you had to learn derivatives completely before you can do L'Hopital's. So now's the time to learn it. So a lot of the things I'm going to talk about initially in this first notes section is going to be review, things you need to be able to remember in order to solve these. And then we're going to start seeing these three types of questions back to back, and you're going to have to be able to tell which one it is. Okay? This is known as one of those relatively easy lessons, so no stress. Here we go. So first thing I want to recap is a lot of times these errors that make you have to do L'Hopital's happen when fractions have asymptotes. So let's go over these functions with asymptotes. We have rational functions, which is a fraction function. And anytime you have 1 over x to an odd exponent, you do have two asymptotes, okay? And then I always call these the elbows graphs, are on opposite corners. If this was negative 1 over x to an odd, then they would just be on opposite corners. If I have a function of 1 over x to an even exponent, again we have two asymptotes, one horizontal, one vertical, but both elbows are on the top. And if it was negative 1 over x to an even exponent, then they would just both be on the bottom. Okay? Now, specifically finding those asymptotes. So horizontal asymptotes is probably the more complicated one. You're going to analyze the terms with the highest exponents in both numerator and denominator. So if you have like a long polynomial on the numerator and denominator, just look at the term with the highest exponent. And then you pick those two out, and you're going to compare the exponents. If the exponent in the numerator is greater than the one in the denominator, then you have no horizontal asymptote. If they're the same, like let's say they'd both be squared, you would use the numbers, the coefficients, a over b, as the location of your horizontal asymptote. And if the exponent in the denominator is greater than the one in the numerator, then you have a horizontal asymptote at y equals 0. Okay? Again, this should all be recap. We talked about this in limits, and you learned this in Algebra 2. Vertical asymptotes are found by setting the denominator equal to 0. Remember to be careful with that, because if you can cancel it out with a binomial in the numerator, then it's a whole and not an asymptote. If you need a recap on that, take a look at our review notes that we did at the very beginning of our limits chapter, okay? Now, something else we talked about when we learned limits. Fractions involving infinities. If you have infinity over a number, remember this fraction is top heavy, therefore it equals infinity, okay? If you have infinity on the bottom and a fraction is bottom heavy, then the fraction equals 0. Okay, so think about a massive, massive number over a tiny, tiny number, okay? And then think of a tiny, tiny number over a massive number. Now, if we have infinity over infinity, it's the same thing as if we had like 0 over 0. These are called indeterminates, okay? This is the scenario that we're going to be able to use L'Hopital's to solve, and you're going to learn that rule shortly, okay? Now, let's talk about other indeterminate forms. I think it's kind of difficult to know the difference between the two. They're very similar, which is why I made you a chart here. So this top row are your indeterminate forms, okay? Now, the two that you will see most common in calculus is 0 over 0 and infinity over infinity. So those are the two that I really want you to stress about, okay? These are other forms, and you'll probably see these once in a blue moon, like in BC, in Cal BC, okay? So don't stress about those. Now, these four here are not indeterminates, okay? Infinity plus infinity is infinity. Negative infinity minus infinity is negative infinity. 0 to infinity is 0. And 0 raised to negative infinity is infinity, okay? Again, these two here are very rare. These two are the more common ones you might see come up, okay? So, for example, if I said like infinity plus 5, we can assume that that still just equals infinity. Now, L'Hopital's rule. Here's what's new today. And this is probably the easiest thing you'll ever learn, okay? If the limit of some rational function, meaning a fraction function, gives you an indeterminate, 0 over 0 or infinity over infinity, the two that we said we're going to be seeing. Then you can solve that limit with that same exact value by doing the derivative of the numerator over the derivative of the denominator. Now, please do not mistake this with quotient rule. Okay, quotient rule is low D high, high D low. This is just doing the derivative of the numerator over the derivative of the denominator. Okay, so we're going to start seeing a combination of questions that take all of this into account. And we're going to be seeing a lot of limits today, okay? So let's see the first example. All right, so if we look at this first question, it says the limit as x approaches infinity for 3x squared over x squared plus 1. Your first step in any limit, what you learned back in chapter 1, is to always plug in the value first. So if I plug that in, I get 3 times infinity squared over infinity squared plus 1. Okay? So infinity squared times 3 is still infinity, and infinity squared plus 1 is still infinity. This is an indeterminate. Okay? So I've got a few options here. The newest one that you learned, L'Hopital's, is definitely going to be the fastest version. Okay? So L'Hopital's says that I can redo this limit to the derivative of the numerator and the derivative of the denominator. So the derivative of the numerator would be 6x over 2x to the first, and then derivative of 1 is 0. If I plug in infinity here, I get 6 times infinity over 2 times infinity, which again gives me an indeterminate, which every time I get an indeterminate, it is like a passageway that allows you to do L'Hopital's, okay? So every time I get indeterminate, I can do it again. So now the limit as x approaches infinity, derivative of 6x is just 6. Derivative of 2x is just 2. The limit of any constant, I have no variable to plug infinity in, okay? So the limit of any constant is just that constant. And 6 over 2 equals 3. And that is my answer here, okay? So the reasoning behind why the answer is 3, back in the day, like I want to tell you about 5 years ago, L'Hopital's was not allowed on the A/B test. You had to do it algebraically. Then they started allowing it, and the shortcut was allowed. So if you do this algebraically, okay, we see here that we have to analyze asymptotes, okay? The denominator, set equal to 0, will tell me my vertical asymptotes. So x squared equals -1. X equals square root of -1. That gives me an imaginary number. And remember, we don't have imaginary numbers on our regular graphs, on our x and y coordinates. So that means that there is no vertical asymptote. And now if I check horizontal asymptote, okay, the exponents are the same. They're both squared. So my horizontal asymptote is that y equals a over b, 3 over 1, okay, which is just 3. So that means that this graph has some sort of a horizontal asymptote at 3. Now remember, anytime we have some sort of an asymptote, we know that the function is going to ride along that asymptote, which means my function either happens up top, and as I go out to infinity is going to shoot out on that asymptote, or it'll happen below it. Okay, but we will always approach asymptotes. A quick way to check is by plugging in an easy number. If I plug in 0 into my original function, I get 0 over 1, which is 0, which means there's a point here, which means somehow this must approach the asymptote. Okay, maybe I don't know what else happens. I'd have to plug in some more points. But you can see that as I go towards positive infinity, my y value approaches that asymptote of 3. Okay, but again, you don't need to do this work. This was just me giving you a visual. As soon as you get your answer through L'Hopital's, you can stop. All right, let's look at these next few. Okay, the first one, remember my first step in any limit question is to plug in that limit. So I can say 5 minus 2 over infinity squared. Okay? That leaves me with 5, right? Because the limit of any constant is just a constant. Minus, if I have a fraction, a number over infinity, that just equals 0. That is bottom heavy. So my answer to this one is 5 minus 0, which is 5. Notice I did not even need L'Hopital's here because I did not end up getting an indeterminate. L'Hopital's is only allowed if you get an indeterminate. So for example, on an AP test, if the work consists of doing L'Hopital's, you need to be able to prove that you get an indeterminate before you can continue, okay? Let's look at this next one. Plug in the -1. Can already easily see that denominator is going to be 0. This gives me a positive 1, so I end up with 2 minus 2. Here's my indeterminate. Now I'm allowed to do L'Hopital's. So derivative of 2x squared is 4x. Derivative of -2 is 0. Derivative of x is 1. And derivative of 1 is 0. Okay? If I plug this in, I get 4 times -1, which gives me -4. And there's my answer. So in chapter 1, when we were approached with these questions, you had to clean all of these algebraically without doing the shortcut. So for example, you would have factored out a 2 and had x squared minus 1. X squared minus 1 would have been a conjugate binomial, which could have turned into x plus 1, x minus 1. You would have canceled the x plus 1s. So it would have been a little lengthier and more algebraic. Here you have this nice little shortcut. Let's check this one out. 3 times infinity squared minus 1 over 2 times infinity squared plus 1. Well, infinity squareds times a number is still infinity, and if I subtract or add 1 from infinity, they are still infinities. Okay? So here's an indeterminate. I can do L'Hopital's now. Derivative of 3x squared is 6x. Okay? Derivative of -1 is 0. Derivative of 2x squared is 4x. Okay? We kind of saw a similar question up here where we plugged in the infinity, got indeterminate, and did it one more time. I'm going to show you a second method. Before you do this limit, you could reduce that fraction. Okay? And it will save you some time. So I can say this is the same as saying the limit as x approaches infinity. If I reduce, I can reduce those x's. And if I reduce 6 over 4, which I could leave it as 6 over 4 because in Cal, remember, you do not have to reduce numbers. But you do get 3 over 2. And now the limit of any constant is just that constant. So do know that you are allowed to reduce whenever you want, okay? If I would not have caught that reducing of those x's, I would have gone infinity over infinity again. And then derivative of 6x would just be 6, and derivative of 4x would just be 4, and then I'd get 6 over 4, which reduced is 3 over 2, okay? All right, so let's look at these next few questions. Anytime you have these infinities, I know you can go through the whole process of L'Hopital's, but the process of horizontal asymptote rules is going to work very similar, and the top heavy and bottom heavy. So for example, when I see this question, I see that the highest exponents on both are the same, okay? Horizontal asymptote rule says that I'm going to look at the coefficients. So just by looking at this, I know that every time I do the derivative, it'll give me infinity over infinity until I get rid of these. And because they have the same exponent, I will get rid of those x's at the same time. So again, horizontal asymptote rule says same exponent, look at the coefficient. I already know the answer to this is going to be 2. But let's go through the motions. Just a little shortcut to help you through it and make you realize what the answer is so that you're certain, of your answer. Okay, we get infinity over infinity. We proved that we have an indeterminate, which is necessary. Derivative of 2x minus 1 is just 2. Derivative of x plus 1 is just 1. The limit of any constant is just that constant. And you can see that we came out with the answer 2. Now, for these next questions, again, this was discussed back when we learned limits. I know that was a while ago, so I'll recap. Anytime we have a radical, remember, like horizontal asymptote rules, we want to compare just the first term, the highest in the numerator and the highest in the denominator. So if I am just analyzing the 3x and the square root of 2x squared. Now, I'm not allowed algebraically or mathematically to split up a radical, but again, just for the sake of this limit question, I am allowed to analyze just the first terms. This really cleans up to 3x over square root of 2 times square root of x squared is just x. So now I can see that I have both of them are to the same power. They're both to the first. So based on what I showed you here, horizontal asymptote rule says that when they're the same, there's a horizontal asymptote at 3 over radical 2. And I know that limits and functions will always approach those asymptotes. Now if I finish going through the motions of plugging this in, 3 times infinity is just infinity, and square root of 2 times infinity is still just infinity. So I'm going to come down here. I know that I get infinity over infinity, which is an indeterminate. And now I can do L'Hopital's. So the derivative of 3x is just 3, and the derivative of radical 2x is just radical 2, and the limit of any constant is just that constant. So again, I got that sneak peek as to what my answer was going to be all the way in this step, but completing L'Hopital's, I was able to confirm it. Okay? Let's take a look at this one. Same thing, I am allowed to, it's not that it's equivalent, but I'm allowed to analyze the first term, or the term with the highest exponent in the numerator, happens to be the first term here, and the term with the highest exponent in the denominator. Okay? I can continue cleaning this. Now, I know that this is going to end up working out the same as the last question. The only difference that this question here has is that I'm doing it the limit as x approaches negative infinity. Now, we had learned a rule back in limits that if I plug in a negative infinity into an odd exponent, then the negative remains. If I plug it into an even exponent, then the negative disappears. So if both of these were squared, then I would have the same exact answer. Okay? But because I have an odd exponent, I'm going to keep the negative. So we already know that my answer is going to be a negative. I have the same exponent, so it's a negative, and then the coefficient. I'm going to go through the motions of showing the work. Okay. We have my indeterminate, infinities over infinities. So now I can say L'Hopital's. Oops, I forgot my negative there. Derivative of 3x is just 3. Derivative of radical 2x is just radical 2. Okay, and because those were odd exponents, the answer here is going to be a negative 3 square root of 2. Okay. All right, let's check out the next examples. So back to the rule we were just talking about, the exponents and whether the infinity is positive or negative. When I plug this one in, I'm saying infinity cubed, which is just infinity. Here I'm saying negative, I'm plugging in a negative infinity cubed. So since 3 is odd, I keep the negative, okay? So two questions that look identical. If this same question would have been given, but it was x squared, I'd put infinity squared is infinity, negative infinity squared, 2 is even, so I would get rid of the negative, and this answer would have also ended up being positive infinity, okay? So now, let's throw some trig functions in here, okay? The trig functions, back in pre-cal or trig, you learned what the graphs of them look like. Those are very, very useful for these. You should either have a formula sheet that I've given you with those graphs, or you could always go back onto my YouTube channel and watch the videos of what those graphs look like. If I plug in sine of infinity, I don't know about you, but I wouldn't know how to calculate that, okay? I know my basic sine values from my unit circle, and that's about it. But if I analyze the graph of sine, I know that sine goes over and under, and it keeps on going over and under, and it'll keep doing that in between 1 and -1 in both directions, right? Okay? So when you zoom out and you look at this on the grand scale of this continuing to happen forever and ever and ever, this continues to bounce, 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 bounce. And if you remember when we learned limits, whenever a function bounces forever, we call that oscillating. Okay, so since this function oscillates, meaning it bounces forever uncontrollably, then this would be one of the 3 examples that we said a limit does not exist. Okay? So again, knowing the graphs helps. That would be true for a sine function and for a cosine function. It would not be true for the other ones, tangent, cotangent, cosecant, and cosecant, because those have asymptotes that break up the bounds. Okay? All right, this next question, the limit as x approaches infinity. Again, you can start doing everything by hand and cleaning, but if I start thinking about my horizontal asymptote rule and my fractions with infinity, if I put infinities here, this top, the highest exponent is a 2, and the denominator, the highest exponent, is a 1. So this is a top-heavy question, which means just by looking at it and seeing that this is a top-heavy function, I know that my answer is going to be infinity. Top-heavy fractions with infinities always equal infinity, and bottom-heavy fractions with infinity always equals 0. So I know it's going to be infinity. For those of you that are like, why? What in the world? How did you just get to that? Let's go through the motions. Okay? If I plug it in, I get 2 times infinity squared minus 4 times infinity over infinity plus 1. And this is going to give me an indeterminate of infinity over infinity, which means then I can use L'Hopital's, which says the limit as x approaches infinity. The derivative of the top would give me 4x to the first minus 4 over derivative of x is just 1. Okay? So now I have 4 times infinity minus 4 over 1. That gives me infinity over 1, which equals infinity. So we saw it using our shortcut of knowing top-heavy, bottom-heavy, and horizontal asymptote rules, and we saw the work with L'Hopital's. In our next question, I cannot think about top-heavy and bottom-heavy because that only works for infinities. This is a number, so here I'm going to have to go through the motions. Step 1 is always to plug in. So negative 2 squared is 4, times 2 is 8. 8 minus 2 is 6. 6 minus 6 is 0. And negative 2 plus 2 is also 0. Here is my indeterminate. Okay. Moment I have an indeterminate, I can do L'Hopital's. Derivative of 2x squared is 4x. Plus derivative of x is 1. Derivative of negative 6 is 0. Derivative of x plus 2. Derivative of x is just 1. And derivative of 2 is 0. So anything over 1 is itself. I don't have to worry about that denominator. So I'm really saying 4 over negative 2 plus 1. If you want to still put the over 1, you can. 4 times negative 2 is a negative 8. Plus 1 gives me a negative 7. Okay. Moving on. So this next question. I hope when you guys see this question, you don't think about plugging in that 0. Back when we learned limits, you learned 2 special trig limit rules. And hopefully this one sticks out like a sore thumb as a red flag of one of those special trig limits. And the first special trig limit that you learned was the limit as x approaches 0 of sine of some number times x over some number times x. So when you guys learned it, it was like sine of ax over bx, and your answer was just always a over b. Okay? So hopefully if you remember that this is a special trig limit, you know that your answer is just 6 over 4, or you can call that 3 over 2. If you forget that special trig limit rule, you're not done for. Let's check this out. Sine of 6 times 0 over 4 times 0. Okay, I'm plugging in the limit now. I hope you don't waste time on this, but again, in case you forget, the work will still give you the right answer. 6 times 0 is 0, and sine of 0, according to your unit circle, is 0. 4 times 0 is 0. This is an indeterminate. Okay, I can do L'Hopital's. So the limit, as x approaches 0, the derivative of sine of 6x, this is a chain rule. The derivative of sine is cosine. Rewrite the inside. Times derivative of the inside. Derivative of 6x is just 6. I'm going to put it up front. Over derivative of 4x is just 4. Okay? So I have 6 times cosine of 6 times 0 over 4. 6 times 0 is 0. Cosine of 0 is 1 according to my unit circle. So I have 6 times 1 over 4, which is 6 over 4, or 3 over 2. So again, when you're taking your AP test, you guys are timed. And these are supposed to be your shortcut answers that you can save time on and save for the hard questions. So I'd hope you'd catch that this is a special trig limit and not go through all this. But again, you could get it right still, okay? All right, here's an infinity question, which means I can go faster and check top or bottom heavy. And then if it's the same, use horizontal asymptote rule. My numerator has the highest exponent of 1, and my denominator has the highest exponent of 2. Meaning, 2 ways more, this fraction is bottom heavy. If I'm working with infinities and it's bottom heavy, the answer is going to be 0. Let's show the work behind it, okay? Because when you're on multiple choice in the AP, you can go that fast. If you're on an FRQ, you are going to have to show some more work. So, plug it in. You end up with infinity over infinity. Here's my indeterminate. I'm allowed to do L'Hopital's. Derivative of 2x is 2. Derivative of 1 is 0. Over derivative of 4x squared is just 8x, and derivative of x is 1. So I have 2 over 8 times infinity plus 1. 8 times infinity plus 1 is just infinity. So I have 2 over infinity. And now you can clearly see that this is a number over infinity. This is bottom heavy, so this equals 0. Again, I'm giving you the shortcut, and I'm giving you the longer method with all the work. All right, last question. Okay. If I were to plug in 0 here, I would get square root of 25 minus 0 squared over 0 minus 5. Okay? I would end up with 25 minus 0 is just 25, so square root of 25 over 0 minus 5 is negative 5. Square root of 25 is 5. 5 over negative 5 is just a negative 1. The reason why I saved this question for last, if you're gotten into the habit of pausing and trying it before you watch me do it, is because not all limits are that complicated. Don't skip the first step that I always tell you of just plugging in the number, because sometimes it is as easy as just plugging in and getting a number out. You do not do L'Hopital's or any of those crazy other methods until you find that you have an issue. Okay?